All right. So I'm gonna. What am I gonna do? I'm gonna. All right. So the first one. Let me get a little closer here. All right, classwork 3. First one, we have a module. Okay. Ready? 1, 2, 3. 1, 2, 3, go. Okay. So you have some LG panels. Okay. This spec is on Moodle. So let's go ahead and pull up that spec. Let's see. LG. It's under your homework 3 and classwork 3 resources right here. Okay. So it's this panel right here. LG 360 watt mono panel. We looked at this, not yesterday, Monday. So we'll pull that up. Oh my goodness, mine is taking so long to download. LG 360 watt mono panel is the one that you need to take a look at first. Under classwork and homework 3. My goodness. Wonder if I've already downloaded this somewhere. Yeah, there we go. That'll work. I don't know. I've had so many computer problems today. Okay, so I'm gonna scroll down here. So we're gonna take a look at some of these parameters. Let me get to my page here. And I'm just gonna do this first problem. Okay, so we have, so it has a rating of 360, right? That makes sense. So the power, the nameplate rating is 360 watts. And then it says calculate the approximate power loss at STC due to resistance of this tabbing. Okay, first of all, let's talk about what tabbing is. Okay, so solar panel tabbing. Let's look at some pictures. Oh my goodness, this internet is so slow. Come on. Okay. All right. So solar panel tabbing. Here is a great example right here. So this picture, so this is your panel. Those spine lines, those are your charge collectors. And then this wire right here is called tabbing.
Not the thing, bus bang.
This is also called a bus bar. They are flat wire, so they come in a spool. Here's an example. Notice that this is flat. Okay, so these run in parallel, connecting the solar panels, so they daisy chain them together. So like right here, they actually go over, under, over, under, over, under. And what happens is all of these panels, they are connected in series, but these runs. Okay, fine. Okay, I know. They run in parallel. So, for example, the more runs you have, so let's say you have 3 of these runs here. Okay. You are going to have less resistance, okay, from the tabbing, but you're going to be covering a little bit of your panel or your cell, okay? So you're going to be adding just a little tiny bit of shading versus 2 of these where you're going to experience more resistance, but you have you've gained a little bit of area on the top of your cell. And we know that current out is directly related to how much you're collecting from the sun. Okay, so this is the tabbing. So the question is, so you have calculate the approximate power loss. So you have some power loss due to the resistance of those tabbing wires. So at STC is what? What is it? Ooh. Standard test conditions. So it is what the conditions that the panels are tested to in factory. Okay. So those ratings are on spec sheets for panels. So it gives the resistivity of the tabbing. All right. And so we have to figure out how much power loss we have. Okay. So if we have, so I'm going to switch over to start out a new, where do I want to do? Photovoltaics, spring. I have a notebook here for us. Photovoltaics, spring 2020. Okay. No. Okay. So, I know I disconnected it when I was moving it around. Hold on. Yeah. I think I can just unplug it and plug it back in. That's the fix for it. Turn it off, turn it back on. Check it out. Okay. Yeah, I will. Thank you. How about like that? Better? Cool. Alrighty. So okay, so you have this. Let me get a pen color. Start with red here. So this is one. So you have this tabbing, and it kind of looks like this flat rectangle like that, okay? And that's what your current's running through, and this is saying that the thickness here is 0.1 millimeters. Width here is 1.5 millimeters. Okay, so we know that, so our resistance is equal to resistivity, because notice resistivity, the unit is in ohm meters, okay, times the length. So when I say the length, I mean the length of the tabbing that's running through your whole panel, okay? So it's intersecting each cell. So we'll figure that out in a few minutes, but I'm just going to say length, okay, and that's going to be in meters over your cross-sectional area, cross-section area, and that's going to be in meters squared. So it'll end up, yes, with ohms, and that's exactly what we want. Okay, so we are going to figure out the resistance of one run. So let's see here. So let's look at the area really quick of each cell. So if we go back to where we were, which is, okay, this guy. All right, let's go find the cell measurements here. So, yeah, there we go. So, right where it says cell dimensions under mechanical properties. So you have 161.7 millimeters by 161.7 millimeters. So it's a square cell. All right, so we'll go back here. So we have 161.7 millimeters times 161.7 millimeters. That's our measurement cell dimensions. Okay. But we only care about really just one of these because we just need to figure out how long this tabbing is. Okay, so how many cells do we have in this? We have 60 cells. 6 times 10, 60 cells in this panel. So we're just gonna say 60 cells, okay, per module. All right, so our tabbing will cover those 60 cells. So that means 60 cells times 0.1617, sorry, 7 meters, because I changed it for millimeters, is equal to about 9.702 meters for one run length. Okay. So our resistance now, so we're going to plug in what we know up here. So I'll rewrite it. So we have resistance is going to be equal to 9, so our resistivity, first of all, 1.372 times 10 to the negative 8 ohm meters times our length, which is 9.702 meters, over our, what am I doing? Oh, cross-sectional area, which is going to be real small. It's 0.0001 meters times 0.0015 meters. Okay, because we know we're taking that from this right here. Cross-sectional area of the tabbing. So the units will cancel out, and what we'll end up with is about 1.1157 ohms per run. Okay. Cool. And so we could just say, we'll just say R1. R1 is that. Okay, that's one run. And then R2, so 2 runs. So when I say 2 runs, I mean, if I go back here, this would be a string of cells that has 2 runs. Okay, the blown up picture that has 2 runs. So those are wires that are in parallel to each other. Yes, you are correct. So 2 runs equals R2, which equals 1 over 1.1157 ohms plus 1 over 1.1157 ohms. So that will get you 0, oops, I'm sorry, over 1, right? Because we're adding in parallel. So then R2 is equal to 0.557 ohms. We do the same thing with 3 runs. So 3 runs is equal to 1 over R3 equals 1 over 1 plus 1.157 ohms plus 1 over 1.1157 ohms. Whoa. Ohms plus 1 over 1.1157 ohms. So your R3, that's going to be about a third of an ohm or so, just because that's the way it works out. 0.3719 ohms. So then we can take a look at the power loss, because that's what it's asking us about. So for one run, we'll use the, we won't use the ISC because that's kind of an extreme current. We'll use the maximum power point, which is where the cell will be producing most of the time. So if we go back to the our, there we go, our spec. And remember, it said STC conditions, so we have to go to the STC electrical properties, so that would be right here. So our MPP current is about 9.787, excuse me. So let's see if I can write on this actually. So I'm looking right there. Okay. All right, so I'll go back. So that's the current that's running through the tabbing. So I'm just going to say at SPC, IMPP is equal to 9.87 amps. So we know power is equal to current squared times R. So we can just do that for P1 is equal to the 9.87 squared times our R1, which is about 1.1157 ohms. That's 2. And that's equal to 108.688 watts. That's your loss if you do 1. Okay? So P2 would be exactly the same, where you have 9.87 squared times that 0.557 ohms, which is going to be about half 554.2612 watts. And then P3, same thing, 0.3719 ohms, which is equal to 36.2293. Okay, so you can see, of course, that the more runs you add, the less loss you have. Do you have a question, James?
108.
88. Swiss cheese.
I don't know, man. It could be an I.
Yeah. Okay. So that is. I'll switch back in a second. Where am I going over here? There we go. So that's the answer. Those are all the answers to number 1. Okay, that's all it's asking for. So that just gives you an idea of basically what they do for solar companies is they optimize how many runs versus the loss you'll get from the runs. Okay, so they optimize it. That's how part of the element of design for solar panels. Okay. So now we're going to get into stuff what you'll need to use for your project. Okay. Part of what we need to know is we need to know the worst case scenario coming from your panels so that we can size the inverter or charge controller downstream. Okay. So we do that by looking at our VOC, our VMPP, all of those parameters that you are working on in the lab. That's what we use. Okay, so number 2 kind of has to do with that. So it says for modules specified, so you have Kyocera and you have your LG. Both of those are in the folder that says week 3. Okay. Resources. It says calculate the highest string voltage under the following conditions. You have 12 modules in series, open circuit, lowest ambient temperature, highest ambient temperature, and you're supposed to show your work. Okay, what does all of this mean? Well, first of all, lower temperature, I think I said this before, it will increase the voltage in your panels, meaning that you're going to have a higher output. Now, that's great. But you want to make sure that that output is going to play well with whatever is downstream from your panels. Okay, so we're going to look at the worst case scenario. So we need to look at the highest voltage. That's what it's asking for, the highest string voltage. So open circuit, which is VOC, would be your highest voltage. We already know that already. And then we're going to take into account temperature, which will raise that voltage. And then we also have multiple in series. So that we need to take into account. So the first one, bless you. Okay, so we'll go down here. Do a different color. Should I do turquoise? I knew you'd want that one. Okay, so this is number 2. It's a fat pen. It's okay. All right, it's saying calculate the highest string voltage and when it says string means that they are in series, all these modules. Okay, so it says calculate the highest string voltage. You have 12 modules in series. Okay. You're looking at open circuit voltage. Oops, circuit without the E on the end because there is no E in. Circuit voltage. And then you're looking at the lowest temperature, and then it also gives you the highest temperature. Now, here's the trick. Highest temperature does not matter if you're looking at the highest string voltage. That is a red herring. It doesn't matter. Okay, so that 90 degrees, we don't care right now. Okay, we care about the lowest temp. Okay, so the lowest temp is going to be that negative 20 degrees Fahrenheit. Okay, so now let's look at the Kyocera first. So Kyocera, oops, Kyocera. So this is 320 watt. Alrighty, so first of all, we need to go back to this Kyocera spec sheet. I want to not highlight everything. Undo that. Pan. Just want to pan. There we go. All right. So we're going to go down to here. Oh, this is algae? Oh, no. You're right. Thank you. We'll get back to this one. All right. Good call. Good catch. Kyocera. Next one. Here we go. Kyocera. This one's way easier to read anyway. Okay, so notice that this right here, that's in Celsius. What do we have? Fahrenheit. So we need to change that. That's the first thing we need to do. So units are important. So we have a negative 20 degrees Fahrenheit, which is equal to negative 28.8 Celsius. Okay. No, I definitely don't have this in my notes. That would be nice. I wish I could do that, but I can't. Okay. I did not make the questions, surprisingly. But I have tweaked the questions because some of them made less sense than they do now. Okay. All right. So we have the right temperature now. Also, the Kyocera, we'll go back to that real quick. Our BOC, here's the question. Would you use your NOCT or your STC? Now, and let me scroll up here. You have NOCT, which is your nominal operating cell temperature. And I said on Monday that is more of a realistic operating condition. But we are looking for the worst case. Okay, so that means that we'd probably not use NOCT. We would want to use STC. Because notice also that your VOC for NOCT right there is less than your VOC at STC conditions. Okay, so we're going to use the STC one. So 45.5. Yes, I can. That was a lot of information. Okay, so nominal operating condition or cell temperature condition is so both of them are standards. Okay, they test. So these are ratings that they test in the lab. Okay, the idea is you want to have panels. You want to be producing panels that are as identical as possible. Okay, so they have to go through testing. And they test them to a certain standard. And these are the two different standards. You have the NOCT and the STC. Okay, so NOCT is tested at a lower irradiance, meaning lower light. So 800 watts per meter squared. It says it underneath where it says NOCT. And then it is tested at 20 degrees C ambient temperature and that AM 1.5. Okay. Plus, there's a little wind in there as well. So, 1 meter per second, I believe. So that testing condition yields less, basically a smaller output. Okay, because it's lower light. But it is a more realistic output if you're going to put your panels on your roof. Now, the STC ones, those are ideal, perfect conditions, and they're likely you're not going to see that kind of output most of the time. Okay, but we use it to design with. Okay, because we want to take a look at the work. And when I say worst case, and I say worst case scenario, but it really would be the best case because you're getting the most out, right? But when I say worst case scenario, I'm talking about you not wanting to overload the components downstream with all of this power.
So that's why we're using the STC.
That's why we're using the STC. Yes. That was a long explanation, but I felt like I should start from the beginning. Okay. So that's why we're going to use the STC, because it is a higher VOC. Because the whole point is we want to find the highest string voltage. So we're going to use the STC VOC is equal to that 45.5 volts. Okay? And if we go back one more time, another thing that we can see if I pan down here is we have these temperature coefficients. So temperature coefficients right here. So let's see, VOC. So this right here, that is our temperature coefficient, and I will show you how to use it. It is in percent per degree Celsius. That means that VOC is going, and I know it's negative, but you'll see why it makes a difference. It's going to go up with a lower temperature. Okay? So we're going to use that in our calculation here. So I'm just going to say our temperature TC, temperature coefficient for VOC, is equal to negative 0.36%, that's a percentage sign, per degree C. I'm just putting down the parameters that we know right now. And our temperature for STC, I'm going to go back one more time. Temperature for STC is 25 degrees module temperature. So that is right here. Right at the top where it says standard test conditions, right underneath it, it says 25 degrees C. That is always true for STC. That is the standard, 25 degrees. But that is the actual module temperature or cell temperature. That is not ambient. Okay, so that's an important distinction. Versus NOCT, which is 20 degrees ambient. Okay, so yeah. Ooh, okay. All right, so our temp, so cell temp, put the M in there, temp is equal to, or I should say at STC, is equal to 25 degrees C. This is degrees C as well. All right, so we have this formula that I'll show you. And this is true for voltage, current, and power, so you can use it all the same way. So I'll show you for voltage. So if you want to find out, for example, the cell temperature, the voltage output from your panels at a specific temperature, you can use this formula. So I'm going to say VOC at, at negative 28.8 degrees C, degrees C, is equal to, and then this is how this works, it's going to be your regular VOC, I'm not going to write the numbers right now, I'll just put it in variables, VOC at STC times 1 plus your temperature coefficient to the power of your cell temperature of your cell, minus the temperature reference. And your reference is going to be this reference. Okay? So it's an exponential change. Okay? So if I fill that in, it's going to be VOC at STC, so that's 45.5 volts times 1. And notice that this is negative, this temperature coefficient. It's also a percentage. So guess what? It's negative 0.0003%. 0.36 to negative 28.8 minus 25. Somebody want to do the math on that? Mm-mm. Try it again.
55.24.
55.24. 55.24 volts. These are. Did you? Oh yeah. Okay. So then you're right. Yeah. Gotcha. Okay. So. All right. So that's cool. So this is for one module. Okay. So we started with 45.5 volts. We went down to a pretty cold temperature and noticed that it increased by 10 volts. That's actually a pretty big increase. Okay. And so now we need to multiply that by 12 because remember there are 12 modules in series. So 55.24 volts times 12 modules. What's that? Anybody? Yeah, 662.88 volts. Okay, so that's your voltage coming off your string. Okay, and 12 is not an unusual installation. Okay, 12 panels. That's about, pretty normal. So, okay. Now, part of this question, let me go back here. It's saying, so that's A. But then it asks an additional question, letter C, do these configurations meet the maximum system voltage spec? So let's talk about that before I move on to the LG one. So system spec, let's go to our panel here. So there is a maximum spec, basically saying you can only have so much voltage output by putting these modules in series. So let me see if we can find it here. I know I have it written down, but I want to see where it is here. It is, here we go. Maximum DC system voltage, 1,000 volts. Okay, so 12 in series, we're still fine. Okay, we could put more if we want, based on this spec. Now there could be other limitations. There are going to be other limitations. Okay, I switch back and forth between what I was saying. Yeah, so there are going to be other limitations because we have an inverter or a charge controller that will hook up, and you'll likely not be able to put the 12 in series. Or I'm sorry, more than the 12. But we'll tackle that when it comes. It'll depend on how large of an inverter you want to buy. Okay, so let's go to the next one. So where I was.
Can you all have
Yeah. There you go. You're welcome. All right. So let's see here. You good? Everybody? Okay. So let's go to the LG one. We're going to do exactly the same thing. Actually, you know what? You guys can do it. Yeah, you can. You're going to do it. Well, you're in class still, so I will, what I'm going to do is I'm going to do it, but I'm muting this. You guys do it, and then we'll go through it. I can just do it like that. Turn it off. You're doing the LG one. The one with the worst spec. You're welcome. It's the STC ones are the ones that are not under the NOCT. So yeah, I think it's cut off the way that they have it.
The thing is, if you actually highlight it, you can see what it actually says. And
does it show you?
Somewhere else, you can see that it actually does say
STC. I know that when I looked at it online, because I downloaded these on offline or from the internet, because that's just where you get them. And you could see the STC, but then the way it is here, you can't see it. So that's kind of unfortunate. Yeah, it is kind of weird. If it's STC, the cell temp, the reference temp is always 25. For STC? Yeah, so the reference for STC is 25 always. Mm-hmm. Yeah. Temperature coefficient is going to be, I'll pull it up. Very bottom. Or, sorry, not total bottom, but bottom of the important information right here. Right. Yeah. Oops. Ah, undo.
The temperature we had earlier, so this and then ERAF is the 25.
All right, you guys ready for me to go over it, or you need a couple more minutes? Okay. Oh man, I should have brought like treats to hand out if you get them right, huh? It'd have to be treats. It'd have to be like a candy bar that I'd like throw at people to get it right. If it's wrapped. If you don't open it in here, I feel like you're okay. You just have to eat it later. Anyway, all right. So let's see how you guys did here. So where am I at here? LG. So I set it up. Here's my thing. Here's my equation. So if I solve that, you get 49.385. Multiply it by 12. You get 592 volts. You have rounding errors. I definitely don't. Right. That's the way. Of course. Well, you would never be wrong. Neither would I. They're both right. That's right. No, we're right. The computers are wrong. So that means that we also have to figure out the max DC voltage. So we go to our spec here. Let's see if we can find it. This one is, again, not my favorite, but there it is. It's 1,000 right here. Right there. Okay. So we're good. Cool. So it is okay. All right. Not too bad. Math isn't too complicated. Now, number 3 is really complicated, and I don't think that it is necessary right now because number 4 is more important and number 5. So we're going to skip number 3 and we're going to move to number 4. So number 4, switch colors, orange. All right, so how much time? Oh, we're good. All right, so me find the question here. So we have a roof, and we have space for 13 LG panels. All right, and we live in Olympia. Our roof faces south, and the tilt, which is the same as elevation, is 30 degrees, and we have no shading. We are supposed to select an inverter from the series that I posted on Moodle, so we'll look at that in a second, and we're going to do a design analysis. Now, you guys don't know how to do this yet, that's why we're going to go through it, okay? So, and it says show calculations for the operating range, the min and the max voltage, the max power level, compatibility, etc. All right, and then resolve any incompatibilities. So, what does all of that mean? Well, first of all, let's take a look at the inverter. So, SMA series is this grid tie inverter right here. So, open that guy up. Okay. So, you know, I don't want to open it up online. I want to open it here. There we go. Okay. Whoa. Why?
If you continue to zoom in, it should
Will it?
go to one page.
Well. Okay. Page display. Single page. Boom. Okay. Here we go. Cool. Get rid of that. All that nonsense. Okay. All right, so we kind of looked at this on Monday. So we're going to use this again. All right. Now, what do we need to think about? We need to think about the inverter because our power is going directly into the inverter. So, if we're looking at worst case scenarios, stuff like that, what is a piece of information that we need to figure out? Yeah. What is another piece of information that we need? We just used it. No. Good point. Temperature. Right, the temperature. We need to look at the coldest temperature in Olympia. So, you know, we can do that. And we can use PV watts to do that because we're gonna look at a typical meteorological year. Okay, so we're gonna use that information. So I'm gonna go to PV watts. PV watts. Okay, we're using it just to get some temperatures here. So I'm gonna go ahead and type in the zip code for Olympia 98501. Go. 98501. And I am not going to care one bit about any of this because all we care about is the temperature. Okay, so I'm just going to go simulate, and I just want to look at the hourly data. So I'm going to download that. The hourly data, the biggest file ever. Our favorite. So close that. Yep, so we're going to find the max and the min. So what you need to do is you need to go equals max, open parenthesis, and then we'll click on the top, and then I'll scroll all the way down.
Control shift down arrow.
Control, okay, control. Uh-oh. I don't have a nice way to do this, so I have my surface, which is makes it a little more difficult. Where the heck's my shift? Dang it. Fine. Yeah. What is the... Oh, 877. Oh, yeah, I can do that. Yeah. What was it? 8778, I think. 18779. 8778. There we go. Cool. Max and then min equals min, and then the same thing.
How does it get over 68?
No. Undo. Undo. No. No. Oh, I need to pull up my... I need to attach a real keyboard. This is not going well for me. Sheesh. Oh, that's because it's all... Dang it. Just when you think technology makes life easier. There we go. You there, right? Okay. Here we go. I know.
Do we really need the minimum though? Because
No.
the minimum would happen when it would be night.
Oh, we need the minimum temperature. Yeah. Oh, at night. We'll do it anyway. Because, well, that doesn't, not always. Doesn't always have to. You can have colder during the day. That's fine. We'll just do it for the total min.
It could also be much, much harder too.
-5 degrees. So this is in C already. So that's nice. So I got 68.2 and -5.
So I'm really questioning when it got to 68.2.
I don't know.
Because that's kind of melting.
16.2 Celsius. What is that in Fahrenheit? Like I said, I can't do these in my head.
150 degrees Fahrenheit.
Wow. Well, remember, that's cell temperature, though. That's not ambient.
Okay.
So that could have something to do with it. All right. Cool. Yep. Was that a paper airplane I just saw?
No.
Definitely not. That would never happen. That looks like your homework. Did I grade this?
It wasn't fine. So grade it on how well it flies.
It better fly well because you're an engineer, so.
Do it.
I will keep this toy up here and give it back to you at the end of class. That's pretty darn funny. Okay. Let's bring it back. Back to where we were. All right. So here we are. So our max and our min. Max temp. So this is question number 4. Max temp for Olympia is equal to or 68.211 degrees C, and our min is equal to the -5 degrees C. Okay, cool. So first of all, let's take a look at our max power here. So that that equation that we used for voltage also will work for power. So you can find P max at -5, which is equal to, and so we're going to look at the output at STC for our LG. So let me pull up the LG here. LG, STC, and everything's yellow. That's great. Okay, so I'm going to undo that really quick. Okay, we're looking at, that's IMPP, VOC, ISC, and then we have our rated output, which is going to be just our name, our 360 watts. Okay, right here. We're going to use that. Okay, so 360 watts times 1 minus, and we need to look at the power temperature coefficient. So I go down to the bottom here to the temperature coefficients. It's a negative 0.37% degree C. Okay, so I already put the negative in here, so 0.0037 times the -5 cell temp minus 25, which is your STC reference temp. And remember, we have 13 panels. So let's say we're going to put them all in series. So I'll just say times 13. So what is that? We have space on the roof for 13 panels.
So 402.34.
I have,
Without the 13.
oh, times, okay, multiply by 13.
5,230.
Yeah, so 5,230 and half of a watt, really, but you get rounded pretty easily. So this is the max PV power DC. So max PV power output in DC. Okay. So if we go back to our inverter spec here, okay, we have multiple models here. We have basically 3,000, 3.0, a 3.8, and a 5.0 size. So they're all different sizes. 3.0 being the smallest. Now, what we have here is we have 5,230 watts output, and we can see that the PV max power, which is right here, okay, right here, that is what we calculated is too large for that model. Okay, so then we go up to the next one, which is right there. Okay, cool. Now let's check out some other information. We're going to find the max system voltage. So that is exactly what we did in the last problem. Okay, so I'm going to have you guys do that. So find the max system voltage. You have the lowest temperature, which is -5 degrees Celsius, and you have the other parameters. So you're going to use VOC at STC.
How did you get the 360 watts?
Oh, the 360 watts. The 360 watts is technically your STC power output. So here, let me show you. It was kind of weird on the LG, but I'll show you here on the other one. It's the same as your power max. So for example, it's where the panel gets its name. So you can see that the panel's name is this 320 watt, and then your STC power max is also 320. So this power max was not listed on the LG, but we know that the power max is whatever it's rated for, which is that.
It's like in the picture on the front.
Yeah, it's up here.
It's on the LG one. It's like underneath electrical properties, but cut off onto the next page.
Oh, is that? Okay, because I couldn't find it, so.
Like maximum power.
Oh, it's right here. Ah, okay, cool. Yeah, so it is on there. I thought that was weird that it wasn't on there. I just knew that it would be the rated value. So 360.
Maybe we should have had the website.
The PDF? All right. Okay. So you guys need to find the max string voltage if you have 13 in series.
My second question was going to be, so you can use the same equation that we did for voltage for
Power.
power?
Yes, and current.
Okay.
Because they all have temperature coefficients that are used exactly the same way.
So the temperature coefficients are all the same?
No. So the temperature coefficients for power and voltage are different. So you can see PMPP. I have a way to write on this. Let me get up. This is what we use here for power. I know, but I could. You have your current VOC. So you just use those respectively for what you're doing.
So now we're doing this.
Yep. For 12. Oh, but not for a different temperature. Yeah. Oh. There wouldn't be any. Maybe not. I would say not enough that wouldn't be lost in the rest of the system. Does that make sense? Yeah.
What?
I was confusing this
I'm recording this lecture, so I'm glad that
Who are you sending it to?
Mark in Idaho. Uh-huh.
Did you just use the power with
Well,
use the power from your I'll be too busy using my life to grow weed.
Can we not?
Thank you, sir.
How much have you had? You just have
None. Not much. Okay.
Okay.
Anybody get an answer? I know that some of you are working really hard over there. What is it? Okay, good.
Wow. Okay, let's stop.
All right. It is 602 volts. Did you say 602?
Yeah.
Chad said 602. Okay. All right. So, if we go back to, so we're good with the power. Okay, we're good with the power rating. You guys get a different answer?
Yeah, I think it should be -0.003.
In the first part,
Yeah.
Okay, Chad, you're out.
All right. All right. So, 602 is the right answer. We know that we're good with the power because we looked at that already, but let's check out the spec for the voltage. All right. So our max DC voltage, 600, meaning that's the voltage from what? From the solar panels. Yes. So we're at 602. That's fine because remember that we used VOC. VOC is, you're probably never going to see that VOC. Okay. Actually, you won't because VOC is more of a theoretical value. Because remember, if you have your VOC value, you have zero current based on our IV curves. And if you have zero current, that means you have zero power, right? So you're not going to see VOC. Okay, you're laughing. All right, so cool. So we're okay. I'd say we're okay. Okay. So we need to check the nominal conditions, operating conditions, to make sure that the system falls below 600 volts usually. So what I'm saying is, I said, okay, yeah, this is fine, but we want to make sure, we want to ensure that when I say that's okay, that's actually true. So let's do that. So what we want to do is we're going to set this up as a VMPP. So this is your operating voltage, okay? Not your VOC, but more of your normal operating voltage. And we're going to say at NOCT, which is a more reasonable operating condition, equals 36.4. How about I add that in there? 36.4 volts. So that is our VMPP at NOCT according to the spec. I'm not going to make it go find it. Times 13 modules. Okay. And it's going to be about 473.2 volts. So that's about where we're going to be most of the time. So, and that's definitely under 600 max DC. Okay, so this is okay. Cool. Now, I'm going to check a few more things. One nice thing is that these modules can all be in series. Now, if for some reason our voltage fell at like 700 volts and the max VOC, the max voltage was still 600, then we'd have to start thinking about having 2 runs in parallel. Okay, so 13 is a weird number because you can't, it's not divisible by 2 or anything, so you can't, or 3, you can have 3 runs in parallel, and you have to have the same number of panels in each run if you're hooking it up to the same inverter. Okay, so it is almost, it's very, very similar to having a weak cell in series with other cells. It basically will throttle the other runs. So you have to have them with the same amount in each run. So if you did have to divide this up into 2 runs, then you would probably only install 12 panels with 6 panels on each string. Okay, but for us, we're good because we can keep it with 13 all in a row. So the configuration would be, you have 13 like that. Okay. What I was saying was you could have, if you had to divide it up, it'd start to look like, that's not a square. These are my, okay, so then they would be 6 by 6. Yeah, so you wouldn't be able to get 13. You'd have to just use 12 because there's nowhere to put the extra one. Okay, so you'll run into this when you do your designs for your project. Okay, because for undergrad, I'm asking you, I'm going to give you a roof with an area, just like this actually, except you have to calculate it. And I'm going to ask you to put as many panels on the roof as possible. And so that you may find that you've got like 17, you can put 17 on there. But 17 is a weird number. You can either put all of those in series, or you're going to have to go down to 16 or go up to 18.
Or put all of them in parallel?
All of them in parallel won't work because your voltage will be too low. It has to fall in this range, and I'll show you in a few minutes. Okay, so anyway, let's keep going. So we need to check. So we have 13 modules in series because we're good with that. So our VMPP at NOCT, which we just figured out right here, VMPP at NOCT is 473.2 volts. Now let's look at the operating range. So the MPP voltage range is back here. Rated voltage range for this model is 195 to 480. Right there. Oops. Which we're good. Yeah, that'll work. So we are still good with this Sunny Boy 3.8 so far. Sunny Boy. So far, so good. All right. So let's keep going here. Now, we need to check for low voltage here. So we know, so low voltage, when would that happen?
When it's dark.
Yeah, 0. So other than when it's dark, when it's really warm, right? When the modules get really warm.
So is 0 actually a problem?
Your inverter will just turn off. But when there's sun out, you want to be able to collect. That makes sense. All right, so we're going to go ahead and use our high temperature. Oops. High temperature V. We're going to use the VMPP because remember, VMPP at NOCT is going to be on the lower side of your voltage. So VMPP at STC is higher than VMPP at NOCT, so you're just going to use the NOCT one. All right. For the lower range. So this is what we just found. That's from the spec. Okay. So we're going to say VMPP at 68.2 degrees C equals your 36.4 volts times 1 minus, and this is your voltage temperature coefficient, 0.27, 68.2 minus 20 degrees. 20 degrees is the reference temp for NOCT, not 25. So important to note that. And then we'll multiply that by 13. Okay, so can somebody calculate that for me, please? $415. Yep, 415.383 volts. If we lose a panel, okay, let's say we lose a panel or something, we're down to 383.431. Let's say a panel is underperforming or something, to just be safe. The lowest threshold of your MPP operating range is 195. Okay, 195. Ooh, right. Oh no, undo that. Wish that I could. There's no undo that's easy to get to. Okay. So I'm talking about that one right here. Okay. So your lower voltage is 195. So what happens if? Huh? Why 195? Your voltage won't. Your current is what really fluctuates, not your voltage, because it does because of the temperature. Let me think about this. Good question. So why 195? Yeah, I guess it only scans in that range. Now, why they put it at 195? If it goes below that, so for example, oops, gosh dang it. If it goes below the min DC voltage, which is 100, let me show you right here. This is the min DC voltage. Then it'll shut off because it has to do, I think, probably the idling power. It's probably just breaking even at that point, so it'll shut off. And if you're operating between 100 and 195, it's not shut off, but it's not operating particularly efficiently. Why they said it that way, I don't know. But that's what's going on. And you can see that it's different based on how big it is, so I have a feeling it has to do with the yeah, the idling, but I'd have to dig into it more to be for sure about it. Okay. All right. So we're at like 383 here, which is greater than that 195. Oops. 195 voltage from the operating MPP operating range. Okay. So we're okay with that. Now, the other thing is we need to check to see if there's going to be any clipping. Clipping means that you reach an AC output, not DC input, but AC output that is above the specification. It will begin to clip the power, meaning it will not output that much power. It will just waste the power. That has to do with the fact that it's a protection against the electronics getting too hot. Okay, and the whole starting on fire situation, which was brought up last time. So, if I go back to my sheet here, so AC nominal, which is AC nominal power, 3,800 watts. That is this number right here, the one that I am highlighting and unhighlighting. Okay, so if your output exceeds that or will exceed that, it will clip off whatever additional it's outputting. It's only rated for that much of an output. Okay, so we got to figure out how much clipping is going to happen, because if you have a system that's going to be above that threshold a lot, then you're going to be wasting a lot of power, and therefore you'd want to size up your inverter. If it's only going to hit that a couple times in a year, no big deal, right? So what we can do is we're going to figure out how big our array is. So, and by array I mean multiple panels. Okay. So we have 13 panels with the nominal watt value of 360 watts. So the total watts for our whole system, you multiply those together, is 4,680 watts, which is equal to 4.68 kilowatts. Now we're going to take this information and we're going to move it over to PV watts. So 4.68, if I open up my PV watts and we'll go back here. This is in Olympia, so I'm going to put in the zip code 98501. We're going to go to that. Okay, again. So now in the DC system size, I'm going to put 4.68. 0.68 kilowatts standard. Going to go roof mount. And we will put, 30 degrees tilt. 30 degrees tilt. Leave the 180 where it is. Okay, and we'll just leave the system losses where they're at. And we'll go to this next page. And we will go to, yes, the hourly. Love that. And what we want to look at is how many times this goes above our allotted 3,000 watts. So what I'm going to do, once I get this to work. So AC output is right here, this line, or this column. Right here. So what I'm going to do is I'm going to make a new column. I'll put it over here so you can see it. I'm just going to say above 3,000. Okay, so I don't think it's probably going to make it very much. So I'm going to do if. So if this is less than, no, if it's greater than 3,000, put a 1. If not, put a 0. Oh, yeah. You're right. Oh, I think I was testing it for the 3,000. Okay, we'll do you're right. Let's do that.
Also, I just did a max of that entire column and got 3623.
There we go. That's good enough. So you could do it the easy way, like that.
Well, that's the easy view. How is that? For DC, right?
Supposed to be for your AC. Mm-hmm. So yeah, you could do the max. That would work. I guess I was in my notes. I think I found that I did have some clipping, but maybe they've updated the data here.
Well, it seems like you used 3,000, not 3,600.
Yeah, I think that's probably what I did. I changed the panels we used last time because they didn't make them anymore. So okay, so Eric, you're saying you just did the max of that?
Yeah.
Okay, let's do that.
But I could definitely see the usefulness of justifying any clipping.
Yeah. I mean, if the max isn't above 3,800, there's no clipping. Right. So if you suspected that there was clipping, then you'd have to do the if statement and see how many times it goes above. Okay. So we're good. Okay, because there's no clipping occurring, so that's great. So we're going to choose that inverter. After all of that, we have secured the fact that that 3.8 Sunny Boy is the one. The 5.0, that's too large. You're going to have more loss. There's no reason to purchase that. It's like having your, truck idling or something. So, okay. What time is it? We have 13 minutes. That's perfect. I need you guys to open up a new program. So I need you to go to System Advisory Model. It is a program that should be on your computers. So,
System advisory.
yes, model.
Can I ask you a quick question?
Yeah, absolutely.
What would we do if the clipping was, how would we know when the clipping is too much?
I would say that if you are getting clipping, probably multiple times a week, that'd be too much. If you get it once a month for one period of time, that's probably not a big deal. I don't have a good rule of thumb for it because most of the time, after you do all the other sizing, you probably are fine. It's just an extra measure to make sure. So let's see. I would say if it's a couple times a year, Dylan, if it's a couple times a year, not a big deal. If it's happening quite frequently, that's a problem. Okay, so if you have this pop-up right here, you can just close it and it'll let you skip it for a certain number of times. And then eventually you'll have to put your email in. Sorry guys, that's the way it goes. But I'm gonna skip it. Yeah. Do you have the same version as I do? 2018 1111?
Yes. Like what?
The reason I ask is that this is updated frequently, and it has various models of inverters and solar panels. So when they produce new ones, they'll update the database. If some are not produced anymore, they'll update the database, that kind of thing. So you want to have the same version as me, because when I grade, it won't be all weird where we have different numbers. Okay, so system advisory model is put out by NREL, National Renewable Energy Laboratory. That is the same group that produces PV Watts. Okay, PV Watts is like a toned down version of this program. This is a free software, so if you want to download it on your own computer, go for it. Just make sure you have the same version as I do. And this is a much more in-depth, moldable program compared to PV Watts. So it actually does a lot of different things. So if you go to Start New Project, it actually gives you a lot of different options. Look at this. We have concentrating PV, biomass, wind. I've never used those, but they're there. We're just going to focus on the detailed photovoltaic one, which is the first choice. And we're going to use residential because that's the project we're going to be working on. Now, when you click on these two, nothing happens. That's because the OK button is way down at the bottom where no one can find it. And you'll just sit there waiting for it to do something and it won't. All right. So what we need to do, so you have some different tabs here. Okay. And I'll talk about most of them. So first of all, the location, let's say we want to do, what does this say? I think it says Olympia, but let's do different, let's just give an example. How about, no, let's do Olympia because we're supposed to plug these in. Olympia, so type in Olympia. I already have mine already in here, but we can, if you don't have yours, see mine says Olympia right here. You can go to download weather file and you can type the location. So Olympia, download and add to library. And it'll just download that. And that file includes all that weather data and stuff that you saw in PV Watts, that typical meteorological year. That's what you're downloading for that location. Okay. So I've got mine here. And all this stuff that's blue, it you can't change it. It's just part of the file that you downloaded, so that's fine. Then you go to module over here, and you have this whole list of different models of solar panels. Okay, so you can sift through here if you purchase one, and it already includes all of the parameters, like right here, PMPP, VMP, IMP, VOC, ISC, temperature coefficients, all of that. So what I would suggest when you're doing your project, because for those of you doing grid-tied system, you'll be using this program. I would choose a panel, and then I would make sure that you can find that panel in this database before you start designing anything. Because then if you can't find it in here after you've designed everything, you're like, well, shoot, now I got to go back and change everything. Okay, so, and the thing you want to check is you want to have that spec, the paper spec in front of you, and you want to make sure that these automatically loaded parameters match the spec you're using to calculate your stuff. Okay, so just verify that before you dive into this. Okay, so for us, I'm going to use, so it's the I'm going to use the panel.
Sunny Boy 3.8.
Sunny Boy is the inverter. So we need to put in our panel. So that is going to be, yeah, LG. Let's see if we can find it. It's in here somewhere. Ah, there are the LGs. Okay. We got an LG 3. Oh, I think it's in the here. It's this one. Nope. Nope. This one. Yeah. LG 36Q1C A5. 3, 6. Is it? Oops. This one. That guy. Okay, so I would, at this point, I would click on this and then I'd make sure that these match up with what I have in the spec that I was using. But you can see all these are here. This is your IV curve here. And then down here at the bottom, we don't really need to change anything. Yeah, so we're fine with that. Then you go to inverter. And then you would choose the inverter. So the inverter should be, I think I gave it to you. It's that S Sunny Boy 3.8 US dash 40. So it should be this one. And you want to check these, especially you want to check the minimum MPP DC voltage and the maximum MPP DC voltage.
Is there like another file we need to download?
For which one? No. Should be this one right here. Oh, wait. Hold on. Uh-huh.
Is it the SP or TP one?
TP.
Okay.
You guys find it?
Yep.
I'm having a harder time here. Oh, there we go. That's it. That's the one. No, it's not. Dang it. TP. SP.
SP 3.8 dash.
That one.
TP dash US dash 40.
Uh-huh. That's it. The reason that this has to be so specific is these parameters right here, they do change.
So it's
SB 3.8-1 TP US 40. 240 volts.
I'm not sure what changes with the TP and the SP.
The letters.
Yeah.
She's got you there.
On a roll today. Okay, and then system design quickly, because I think I'm going to be finishing right on time. Yeah, one inverter, and then you need to, let's see, modules. If you go down to electrical configuration, you're going to put one string, and we're going to put 13 panels. Okay. Fixed axis, and then we have a tilt of 30. South facing. Don't have to change anything else. We'll just leave it all. Shading, we will tackle a different time. It said no shading, so we don't have to worry about it. Losses we'll deal with later. All this other stuff we will deal with later. Has to do with costs and whatnot. So if I go simulate, I go okay. Here are the graphs. So you have your annual energy, and you have, this is important, your annual energy yield. You have also net present value. That's important, but we'll talk about that later. That's more of a financial piece to this. Losses, here's where you're getting a lot of your losses. Reflection, soiling, meaning your panels are getting dirty. Some module mismatch, meaning some of your panels are preventing others from producing as much. Just some other stuff, AC wiring. So, okay, so we are out of time, but you should be able to do this classwork, and I will take a look at the homework really quick to see how much that is. I'm not trying to overwhelm you guys. Anything we didn't do, except don't do number 3. The only thing you have left to do is 5, because we did everything else. And then...
So is 5 just using graphs here?
You're just setting up, it's a little bit, your like we just did, and we're going to take a, you need to put the energy yield first year and then annual yield. You're just answering questions about what you just simulated, then you change it to microinverters and go back and do that. So you're going to have all of the microinverters are in parallel. They're not in series, they're lined up parallel.
So
we just exit out of this?
Yeah, you can do that.
So that would change what our...
Yeah, you're going to need to turn in number 5.
Okay, but we don't like this that we just did. If we exit out now.
Save it.
You can save it.
How do we save it?
Yeah, how do we?
You just go up to save, file, save. No, we're not doing that one. Okay.
I can't.
Here's what's due next week. This is what's due. This is due Wednesday, number 5. Finish number 5, and I need you to do homework number 3. It's not that long. Not that long.
And this is due when?
Wednesday. Homework 3, classwork 3.
We have one more class.
Yes, we'll watch.
Yep. You have Monday.
When we turn this in, do you want all those PV watt?
Like, you're gonna need to work.
No, that's okay.
We never started.
So
I never started that.
for the classwork, you want to throw in everything, or
Yep, turn in everything that you did.
Right now?
No, Wednesday.
and so what we should have left is 5
Mm-hmm.
with all parts.
Mm-hmm.
Okay.
Yeah. We did everything in class except for number 5. Number 3 is gross. I don't want you to do it.
I have a question.
Yep.
Number 1, I didn't catch up with the slide.
Okay.
Can you show it to me?
Oh, okay.
I hope you understand why I don't like most people actually class.
Oh, he drew it with the mouse.
Just like
Wow.
asshole.
So
This is gonna be 66.
I think you're just missing this part right here.
Yeah. Okay.
Yes. Sorry. And I'm sorry if I'm like a little bit snappy. I just haven't had enough food today.
Well, there's like a shit ton of food in our building.
That's my problem.
We're gonna have, well, I assume we're gonna have dinner.
I'm gonna like run this quickly to the dorm to get food and shove food in
Thank
face
you.
before going to the classes in 6 minutes.
Awesome.
Oh, because you have that.
I'm not doing that on an empty stomach. They'll get paid enough.
When does that class get over?
7.
Okay, so I guess you watch and you won't work.
Yeah.
Can I see your notes for
I won't watch you. I'll just watch video on my computer until we
Which
have to
one?
work.
This is the problem.
I assume. What else?
We do the third one.
fourth.
Fourth one. Okay.
Oh, you're gonna rewrite that.
Hold on. I think this is it. 4.
I need to.
Well, I was gonna do.
Do you have any of it? Or you just need part of it?
No, I need part of it, but I don't know which one I'm
Okay.
missing, so I'm just
Make you food and bring it. Pick one of the 3 things. Oh,
Stuff
So
there.
I went to Gabby's to go buy the fuckers work for you. We had Japanese.
That's all? That's it.
Thank you.
Mhm.